A profound and important generalization of the Pigeonhole principle is called the Ramsey's Theorem. So it is named after the English logician Frank Ramsey. This statement is the most popular and easily understood instance of the Ramsey's Theorem. Of six or more people, either there are three, each pair of whom are acquainted, or there are three, each pair of whom are unacquainted. One way to prove this result is to examine all the different ways in which six people can be acquainted and unacquainted. However, napaka-tedious nito. What if hindi lang 6? Paano kung 10, 15, 25? Okay? Fortunately, merong simple and elegant proof that avoids consideration of cases. But before going to the proof of that, we will formulate first the result more abstractly as K6 arrows K3 and K3. So anong ibig sabihin nito? K6 means a set of 6 objects, for example, people, ganon, and all of the 15 unordered pairs of these objects. Bakit 15? Kasi 'di ba yung dalawang tao kasi pwedeng acquainted sila or not acquainted. So that is 6C2 kaya 15. So parang we are choosing 6 points in a plane, no 3 of which are collinear, and then drawing the edge or line segment connecting each pair of points. So the edges now represent the pairs. Parang ganito, yan. Pwede silang acquainted or not acquainted. Basta merong relationship between these two points. In general, Kn means a set of n objects and all of the pairs of these objects. Sa ating graph theory, meron tayong complete graph. So, eto yon. This is an illustration of K6. Acquainted pairs and unacquainted pairs can be distinguished by coloring edges, say red para sa acquainted, tapos blue para sa unacquainted. So if we say three mutually acquainted people, we mean a red K3. Parang ganon. Okay? So similarly, kapag naman sinabi nating three mutually unacquainted people, we say a blue K3. This expression is an assertion that no matter how the edges of K6 are colored with colors red and blue, there is always a red K3. Ibig sabihin, 3 of the original 6 points with the 3 line segments between them all colored red, or a blue K3. This leads us to the Ramsey's Theorem. If m is greater than or equal to 2 and n greater than or equal to 2 are integers, then there is a positive integer p such that kp arrows km and kn. This theorem asserts that given m and n, there is a positive integer p such that if the edges of kp are colored with red or blue, then either there is a red km or there is a blue kn. The existence of either a red km or a blue kn is guaranteed, no matter how the edges of kp are colored. And if kp arrows km and kn, then kq also arrows km and kn whenever q is greater than or equal to p. So if we have K6 arrows K3 and K3, then K7 also arrows K3 and K3. There is also this number, this is called the Ramsey number, R of Mn, and this is the smallest integer p such that Kp arrows Km and Kn. Thus, the Ramsey's theorem asserts the existence of the number R of Mn. And by interchanging the colors red and blue, in fact, R of Mn is equal to R of Nm. The numbers R of 2n and R of M2 with M and N greater than or equal to 2 are actually the trivial Ramsey numbers. So with this, balik tayo sa theorem 1 natin and let's prove the Ramsey's theorem. For our proof, the existence of the numbers R of Mn can be shown by using induction on both integer parameters m is greater than or equal to 2 and n is greater than or equal to 2. So if m is equal to 2, then r of 2n is equal to n. And if n is equal to 2, then r of m2 is equal to m. Di ba nasa remarks natin to kanina? Now, let's assume that m is greater than or equal to 3 and n is greater than or equal to 3. And take as inductive assumption that both r of m minus 1 n and r of m n minus 1 exist. So magsisimula tayo sa 3 kasi nga trivial na yung sa 2n and m2. So let P be equal to r of m minus 1 n plus r of m n minus 1. And show that Kp arrows Km and Kn for this integer P. Since yung P natin dito is equal dito, then we say that P is less than or equal to this plus 1. Siyempre nagdagdag tayo ng isa, so less than na yung P. And we know that P is equal to R of Mn. So R of Mn now is less than or equal to R of M minus 1n plus R of M n minus 1 plus 1. Now suppose that the edges of Kp have been colored red or blue in any way. So let's consider one of the points x of Kn. And let Rx be the set of points that are joined to x by a red edge, and let Bx be the set of points that are joined to x by a blue edge. So, an illustration is like this, para medyo maintindihan natin, no? So, pumili tayo ng isang point, tapos lahat ng red na naka-attach, pinangalanan natin na Rx, tapos lahat naman ng blue na naka-attach, pinangalanan natin na Bx. Then, the cardinality of Rx plus Bx is equal to P minus 1 equals R of M minus 1n plus R of M n minus 1 minus 1. Bakit nag-minus 1 tayo? Kasi yung number of vertices natin ay P. So, eto yon. Pero di ba kapag kinuha natin yung point na yon, syempre i-minus natin siya kasi hindi naman pwedeng i-attach niya yung sarili niya sa sarili niya. So, ang mangyayari is lahat nung naka-attach na red plus naka-attach na B, okay, maliban doon sa isa. Kaya may minus 1 tayo dyan. Which implies that Rx is greater than or equal to R of M minus 1n or Bx is greater than R of M n minus 1. Now, suppose that 1 holds yung cardinality of Rx is greater than or equal to R of M minus 1 n. And let Q be equal to the cardinality of Rx so that Q is greater than or equal to R of M minus 1 n. What does it mean? It means that of all the Rx vertices, we can guarantee an M minus 1 vertices all connected in red and N vertices all connected in blue. If the second possibility holds, then it is done since there is a blue Kn. Okay? So, ipapalabas na lang natin ngayon yung Km. Pero dito kasi M-1 siya. So, kung meron na tayong Kn, paano natin mapapalabas yung Km? If the first possibility holds, then it is also done since there is a red Km-1. And kapag dinagdag natin yung x point na yon to obtain a red Km, then all edges joining x to the points in R are colored red. A similar argument works when 2 holds. So ganun din, we can guarantee in Bx that there are m vertices connected in red and then n minus 1 vertices connected in blue. And if we add the x vertex to the blue, then we have R of m n. So therefore, by induction, the numbers R of Mn exists for all integers m n greater than or equal to 2. Note that if both 1 and 2 failed, then the cardinality of Rx plus the cardinality of Bx is less than or equal to P minus 2, which is a contradiction. For example, if we substitute 3, 3 to this inequality, then we have R of 3, 3 is less than or equal to R of 3 minus 1, 3, plus R of 3, 3 minus 1, plus 1. And that is just equal to R of 2, 3, plus R of 3, 2. Pero alam natin, di ba, na ito, doon sa ating basis step, is just equal to 3. And also this is just equal to 3. Therefore, R of 3, 3 is less than or equal to 3 plus 3 plus 1, or that is less than or equal to 7. What's good with this theorem is that it doesn't only assert the existence of R of Mn, but it also gives you an upper bound for the R of Mn. There is an even more general form of Ramsey's theorem in which subsets or pairs of two elements are replaced by subsets of T elements. So we let K T sub n denote the collection of all subsets of T elements of a set of n elements. Given integers T greater than or equal to 2 and integers Q sub 1, Q sub 2 up to Q sub K greater than T, there exists an integer P such that Kt of P arrows Kt of Q1, Kt of Q2 up to Kt of Qn. In other words, there exists an integer P such that if each of the T element subsets of a P element set is assigned one of K colors, say C1, C2 up to Ck, then there are either Q1 elements assigned to a color C1 or Q2 elements assigned to the color C2 or Qk elements assigned to the color Ck. And this number R of Q1, Q2 to Qk is actually the smallest such integer P in the Ramsey number.